Hello, students. Today we would like to discuss the second derivative. We found with the first derivative that we were able to glean some very useful information about functions, especially increasing, decreasing, and the result that follows from that, which is called the first derivative test. So we have a very convenient way of checking the signs of the first derivative to determine relative extrema. Remember, when you did your prerequisite courses, we did not have that strategy. That is, we used everything we could to get a reasonable picture of the graph and also a reasonable understanding of the function without the use of the derivative. So what we're finding now is that we are able to go back to analysis in the previous classes and add sufficient detail to complete the picture. And so what we find is that all of the tools that we used in the prerequisite courses are still very valuable. But when we add the structure of the derivative, we can fine tune and make our function analysis more precise. So what we're finding is that now, with the use of the calculus, we complete the picture. So what I want to do now is to discuss some new terminology that we will need and how we will actually analyze the second derivative to come up with some new information. So let me share my screen. Just like with all of the newer constructs, we have terminology that we need to set forth and use as we communicate. But I don't think you'll find any of this to be overly complicated. Now, first, we want to speak about what it means to have an upward concavity and a downward concavity. So first, we will start with f, a function to be differentiable at c. And then we will say the graph of f is concave upward at the point c f of c, if and only if there exists an open interval I containing c such that the graph of f is above the tangent line at the point c f of c. So when you think of this, you can think of the tangent line as being here and the graph as curving away, so to speak. That is concave upward, away from the tangent line in the upward direction. So sometimes we can think here that the curve is smiling, or that we have a shape of the curve that maybe sometimes we would infer, but we would really have no reason mathematically for doing it. And you think about polynomials. Many times we will draw the graph of a polynomial in our prerequisite courses and pass along some shape that seems to be necessary, but there's no mathematical justification for it. Well, we're going to see why this shape is actually confirmed by the arithmetic of the second derivative. Now, the second item that we need is a downward concavity. So we're going to say the graph of f is concave downward at the point c f of c, if and only if there exists an open interval I containing c such that the graph of f is below the tangent line at the point c f of c. So again, we have the curve falling away, so to speak, like a frown line from the tangent line. So at least in our definition for the concavity, we need the existence of the tangent line at the point c f of c. That is, f prime of c is defined so we can construct a tangent line. And then we want to talk about the curve having a particular shape in the neighborhood of that c. So again, we're forced to check arithmetic because we're thinking, if the increasing decreasing has to do with the sign of the first derivative, it is most likely the case that the upward or downward concavity would have something to do with the sign of the second derivative. And we see that in the next result. This is called the test for concavity. So suppose f is differentiable on an open set I containing c. And the test is very simple and very straightforward and parallels the increasing decreasing theorem that we have already used. So if the second derivative at C is positive, then the graph of f is concave upward at this point, and we get a situation like this. So again, a positive second derivative at C would give us the conclusion of an upward concavity in the neighborhood of C. And of course, what we would have to do is analyze the sign and just to basically see how big that interval would be. Now, likewise, a negative second derivative would give us a downward concavity at the point C of f of C, which would be as this particular sketch indicates. So concavity, or the test for concavity, is just like doing increasing decreasing. We look at the sign of the second derivative. So again, as we go through the orders of differentiation, we're seeing that the first derivative is very useful to us. Increasing, decreasing, first derivative test. We're now seeing that the second derivative, as far as a shape operator, is very useful to us because it will indicate the actual shape of the curve. That is, as the curve increases, what is the concavity? And we might think to ourselves, there's a possibility, of course, just like with increasing, decreasing, that we could have transition points to go from upward concavity to downward concavity and vice versa. And then, of course, we would want to distinguish that particular point where the concavity changes, just like we think of a peak or a valley, a relative extrema, when we are talking about increasing, decreasing. So let's just say a little bit about why this is true. Let's look at one. You'll find this to be very straightforward and very similar to things we've done previously using the mean value theorem. So let's look at the first hypothesis. Now, because of the preservation of sign and continuity, we can take a delta and just consider a symmetric interval about C, delta to each side. So C minus delta to C plus delta. And that would give us a positive difference quotient. So when we consider the difference quotient that we must use to execute the second derivative, we have this, f prime of x minus f prime of c divided by x minus c. And that quotient will be positive. So that will be our hypothesis. Now, in order to imitate what's going on here, what we want to do is to basically subtract from the function the tangent line equation. So what we've done here is something very similar to what we did with the mean value theorem. That is, we'll set h of x to be the difference between the function f and the tangent line equation. And now what we can do, if we think about this, is show that this function is actually positive. That is, there is space between the curve and the tangent line, which would then give us the upward concavity that we're looking for. So in order to move this forward, we're going to use the mean value theorem. So again, in this case, for the x and the c, we will just take a delta that lives between those two. And then by the mean value theorem, we will have the derivative at, theta, not delta. We will have the derivative of f at theta equal to the slope of the secant line formed by x, f of x, and c, f of c. But of course, now what we can do is multiply by -1 upstairs and downstairs, and then rewrite the f prime of theta as f of x minus f of c divided by x minus c. Now, the key here is that we can cross multiply and then make a substitution for this difference here. That is, f of x minus f of c will just be f prime of theta times x minus c. So that's the very convenient use of the mean value theorem. Now we can go back to our function and do the replacement. So for the f of x minus f of c, we simply replace that with f prime of theta times x minus c. And now, of course, we can factor the x minus c from both. Now, this is where we use our hypothesis. These two factors here form the difference quotient that we've assumed to be positive, and they have the same sign. And therefore, due to the fact that they both have the same sign, this particular quantity will be positive. That is, h of x is positive. And indeed, we will see that in the interval from c minus delta to c plus delta, the curve or the graph of f will be above the tangent line. So that's a very straightforward arithmetic argument that, again, showcases the great importance of the mean value theorem. The mean value theorem is central to what we're doing. As I've said before, it provides the necessary arithmetic between the slope of the secant and the derivative. And that is imperative if we're actually thinking about signs of functions. So again, just remember, as we continue through the course, we will have other mean value theorems for derivatives, and we will also have mean value theorems for integrals. So the MVT will get used and reused. And each time the result will be very important to us. Okay, now we have two other ideas. One is just basically terminology, and the second is an alternative to the first derivative test when it would apply, and in most cases it will. But what we're going to find is that higher order derivative tests tend to be very, very efficient in calculus of several variables. Most students find the first derivative test to be fine for their uses in calculus 1. However, if you have to compute the second derivative to analyze concavity, you may find it easy or straightforward just to go ahead and apply the second derivative test since you have the second derivative computed. Now, the first piece of terminology is very simple. What we want to do, again, is suppose f is a function that is continuous on an open interval I containing c. We need the continuity. And we're going to say that the point c comma f of c is a point of inflection of the graph of f. That is a point where you have a transitioning of the concavity. So there would be a delta positive such that to the left of c, that is c minus delta to c, the second derivative would have a sign that is positive. And then as we proceed to the right of c, c to c plus delta, the actual second derivative will be negative. So what we see is that we have a change in the concavity, and therefore we denote the point cf of c to be a point of inflection, basically a point where we have the transitioning of the concavity from, in this case, upward to downward. So there's nothing special about that. We could certainly go from downward to upward. So in the second part here, we see that for the values of x to the left of c, we have a second derivative that is negative. And for the values of x to the right of c, we have a second derivative that is positive. Therefore, again, the cf of c is a transition point. Now we think of first derivative giving us peaks and valleys, relative extrema. Now we see that as long as we have a point on the graph of the function where we have continuity, we can talk about a point of inflection. Now, of course, when you think about it, we can have infinite discontinuities, right? We can have vertical asymptotes. We can have infinite derivatives where we have a vertical line, tangent line. And we want to think, okay, if we have a point on the graph, we can still infer the fact that the concavity changes, but formally, we really do want the tangent line to exist at a point of inflection. But we can always make certain adjustments to say that the concavity does change. And of course, when we have vertical asymptotes, as you learned in your prerequisite courses, when you studied trig functions and rational functions, certainly as you drew your graphs, there was an inferred shape that just made sense. As the graph would hug the asymptote, a certain concavity would ensue basically as you drew it. And then you think to yourself, well, is that an accurate graph? Does that really describe what is going on? And now what we're seeing with the concept of concavity, that our pictures were actually correct, that they did model what was actually going on arithmetically. Now, one thing that I said before is that if you do compute the second derivative, you have an alternative to the first derivative test. And many times it's good just to practice doing both and see that they both provide the same conclusion. But what we want to do now is, of course, if we're going to use the second derivative test, we would have to have the assumption of the critical number. So for instance, f is differentiable on an open interval I containing c, where f prime of c is 0. That is, we have a critical number. And then we can analyze that critical number. And this goes directly back to the test for concavity. So if we think of the second derivative as being positive, that is, we have a concave upward situation, then the f of c would define a relative minimum. Okay, so when you think about the shape of the graph being concave upward from the tangent line, we have the definition of a relative minimum. So if you think back to that picture, you have exactly what we were thinking about before. So we have the tangent line, we have the ordinate or the x-coordinate c, and we have the graph moving away in a concave upward fashion, which defines the relative minimum. Now, of course, there's nothing sacred about that. We could certainly look at the alternative to this, which is to say, if the second derivative has a sign that is less than 0, then we see that we have the curve sloping away in a downward concave direction, which then distinguishes the f of c as a relative maximum. So if we think back to the test for concavity and we visualize the picture, we have a situation where, again, the graph is sloping away in a downward concave motion, and we have the definition of a relative maximum. So again, the arithmetic is extremely important. What have we done from the very beginning? We look at delta neighborhoods, epsilon neighborhoods, allowing a variable to get close to a particular real number. We talk about inequalities that have to do with analyzing sign. We're seeing that all of this arithmetic is so central to doing the calculus that everything is wrapped up in the sign of a function. And again, that indicates to you why, when you study your prerequisite courses, that you spend a lot of time with inequalities and analyzing functions so that you can actually find the actual boundary values, find the actual critical numbers, find the actual infinite discontinuities so you can check signs. So that is a central technique. And one of the reasons we spend so much time on that in the prerequisite courses. Now, what I wanted to do here was just go through a very simple argument that would legitimize the second conclusion here. Now, of course, just like when we did the test for concavity, if we have a second derivative that is negative, then we can certainly have a delta neighborhood about c for which the difference quotient is less than 0, just like we had before, no different. But the argument is much simpler. So now, of course, since c is a critical number of f prime of c is 0, so this difference quotient just reduces to f prime of x divided by x minus c, and this will have a sign that is less than 0, or a negative sign. So now that is the hypothesis. So we just simply look at what happens when x is to the left of c and to the right of c, and see if that supports the actual relative max. Okay, well, if x is to the left of c, then x minus c must be less than 0. And therefore, for the negative sign of this fraction to be maintained, the f prime of x must be positive. Okay, then of course that would indicate that f is increasing, and we can just extend that to the endpoints, as we know is the case. So increasing. Now to the right of c, x minus c would therefore be positive. And then, of course, if we want to preserve the sign of the fraction or the difference quotient, then that's going to involve the f prime of x, in this case, being less than 0 to preserve the negative sign. So we have this, and then, of course, by increasing, decreasing, f decreases on the interval c to c plus delta. So we increase, and then we decrease. And therefore, we define that the actual relative max, that is f of c, is greater than or equal to f of x when x lies in this open interval about c. So what we're seeing is that to get the second derivative test, we simply are looking again at the sign and applying the definition of the relative extremum. So we get a very, very useful test. But again, that requires the computation of the second derivative. Now, I may add is if the f prime or f double prime of c is 0, then of course this test would be of no use. And so you'd have to go back to the first derivative test. So many students feel that it's fine to just take care of relative extrema using the first derivative test. But like I said before, there are many applications of higher order derivatives for extrema that can come in very handy, of course, in functions of several variables, which you will see when you get to Calculus 3. It'll be called the second partials test, and it's very convenient and a very, very nice use of the theory. What we find is that we extend everything from Calculus 1 to 2 and 3 variables in Calculus 3, and that extension is very elegant and saves us some time. So we really do have to know our Cal 1 to be able to do well in the Calculus 3. Now what I want to do is talk about some examples where we apply these techniques. Now, the first example, if you think back to your prerequisite courses, lots of time was spent on rational functions, polynomials, trigonometric functions, where you would often use transformations and analytic techniques that did not involve the derivative in order to support a particular conclusion about a function. So what we want to do now is exhaust all of that. Let's just go through determining ideas about concavity and relative extrema by analyzing the second derivative. And so in this particular example, we will have f of x equals x to the fourth minus 3x cubed. And what we want to do here is just analyze the second derivative. Now, what I want to do when we analyze the second derivative, we're thinking concavity, and we'll just abbreviate second derivative test. Now, I still want to say something about the first derivative and analyze that and make a comparison. Remember, in order to use the second derivative test, we need critical numbers. So we've got to work our way through the function, through the first derivative, and then to the second derivative. So these problems will necessarily take more algebra, but the techniques are the same. We're always looking to analyze sign. Now, first, what we're going to notice in this particular case is that we have no restriction on x. So the domain of f is all real numbers. So when we look at this, we're fine. We're not restricting. We're not doing EBT. So we're just basically back in our college algebra class. Now, I want to make some comments here. We will be doing limits at infinity. and we will be talking about what happens to a function as x becomes positively infinite or positively infinite and negatively infinite. And so what I want to notice first or observe first is, since we have a leading term that has an even power, that is a power of 4, this will be the so-called dominant term. And so we want to observe, at least for now, that the end behavior will be infinity. That is, we'll say more about this in our next lecture, but I want to go ahead and talk about it. X passing to infinity of f of x would now be infinity, because that would be the case of what would happen to x to the 4th as x became arbitrarily large. And then it's a sign convention. As x passes to negative infinity, we can simply replace x with a value that is less than 0. And of course, that negative absorbs. And then, of course, we still tend to positive infinity. That is, when we think about negative infinity, we think about a number that's so infinitesimally small that it is smaller than any negative number that we could come up with. But that is huge in a negative way. And so we still think of negative infinity as being able to consume things. But the idea is that the arithmetic takes over, just like we have with infinite limits. So we assign the value that is plus or minus to the infinity symbol by looking at the arithmetic that's available to us. And so now, of course, this would also be infinity. Oh, well, let me not get too crazy with the infinity symbol yet. Get rid of that. Oh, I gotta adjust the. Here we go. Yeah, the little eraser tape is kind of picky, but that's okay. It's so much better than the old whiteout, I must admit. So again, when you look at this kind of, the light bulb just comes on and says, okay, well, if we're not restricting the domain of the function, then there is no maximum here. We're not going to have a maximum. We could have relative maxima, but this implies no max. They don't exist. We could have relative, but we don't have any absolute. And again, that has everything to do with the fact that it's not even guaranteed. I mean, if we had a closed bounded set, then it would be much different by EVT. So now let's look at the first derivative. So we have, and another thing too, I keep running around here. Let's say f of x, there's so much information to be gleaned. Let's go ahead and factor, in this case, an x cubed from each of the terms in the f, just to make it maybe simpler to evaluate things. That's always something we can think about. Now, f prime, just using the power rule and the linearity of the derivative, we get 4x cubed minus 9x squared. Now, when you look at this, you're thinking, well, we need to figure out what the critical numbers are, so we can analyze this by just factoring a 4 and an x squared. So let's do that. And so that leaves behind an x, and of course, we'll have to divide by 4. So again, 4x squared times x is 4x cubed, and of course, 4x squared times 9/4, the 4's absorb, and we just get the 9x squared with the negative sign, so that works. And so now if we set this to 0, by zero product, if and only if, of course, if x squared is equal to 0, we certainly get x equals 0. So x equals 0, and we have multiplicity 2. So that's going to affect how we check sign. And then, of course, we have or x equals 9/4, and we have a multiplicity of 1. So again, multiplicities are important when we're considering sign tests. So we don't want to ignore that. And it certainly cuts down on the amount of work. So now we'll just go ahead and shift this up a little bit. And I want to go ahead before we get to the second derivative, do all the analysis that we normally do with the first derivative, just to review that and to see how everything fits together. So now we have what? These are critical numbers of f. So we'll go ahead and do a number line. So we have a 0 and we have a 9/4. So now, of course, to make the analysis simple, we can simply take a number that's much larger than 9/4, just take 100 or whatever, and we clearly get positive. And of course, by multiplicity 1, we must cross. And then, of course, when we hit the 0, we just touch because of the multiplicity 2. Again, a very useful idea that you learn in your prerequisite courses that saves you lots of time. So we have plus, we have minus, and we have minus. So of course, this is increase, decrease. So as we move through here, this defines a relative min, which will actually turn out to be a minimum because of the end behavior. This is a relative min by the first derivative test. Relative min is f of 9/4. And then, of course, here, this is one of the conclusions of the first derivative. The sign of the derivative doesn't change, so there's no relative extremum. So this says no relative extremum. The function continues to decrease as you hit this particular horizontal tangent. And so there is no extremum, kind of like f of x equal x cubed. I mean, the function's always increasing. You do have a horizontal tangent at 0, but it doesn't, the increasing nature does not change. It stays, just like the decreasing nature stays here. So we have no relative extremum at 0. Now, like I said before, because if we consider the end behavior here, where we blow up to infinity as x approaches infinity and negative infinity, then this actually becomes a absolute or a minimum. So let's check that value. So f of 9/4, we can just use this. So this will be 9/4 cubed times 9/4. And if you like, go ahead and write the 3 with a 4. So 4 times 3 is 12, just to get a common denominator. And so now, of course, we have an 81 times a 9, which a 9 and a 7 and a 2. So we have 729. And of course, if we cube the 4, we get a 64. And so now when we subtract, we have the 12 from the 9, so that gives us a -3/4. So when we look at this, we're just basically taking 3/4 of this, and if we multiply, what's that going to give us? That'll be a 7 and a 2, so that would be an 8. And then, of course, a 3 times a 7 is a 21, and we carry the negative sign. And then, of course, 4 times the 64 is 256. So we get a minimum value. This turns out to be a minimum of f. And another thing too, as I keep talking about the extreme value, it just means that if you think about this, we don't have anything else to look for. For instance, we know there's no relative extremum here. F of 0 is just 0. I mean, we just know that. We just say f of 0 equals 0. That's easy. But there aren't any other candidates, okay? We know what happens at the endpoints, and there are no other critical numbers to analyze. So this is what forces this relative minimum to be an actual minimum of the function. So now, and of course, if you think about this, as I've written here, let's just go ahead and say the function will decrease here on this open interval. If we just do open intervals, decrease, and then increase. So we can just go ahead and categorize all of this. So we have decreasing. Just go ahead and write down the open intervals of decrease. Just for review, negative infinity to 0, and then of course 0 to 9/4, and then increasing. We'll just have what? 9/4 to infinity. Okay. So again, this would be our analysis of the first derivative test, and this would actually be fine. But what we notice is that we don't have the shape operator of the second derivative. So let's see what that gives us. So let's go back to an easy version. Let's go back to an easy version of the first derivative, which is here. So let's just use this. So we're going to say f double prime of x will just be the derivative of 4x cubed minus 9x squared. Now, when we think about this, again, we apply the linearity of the derivative. And what's important here, we don't have to necessarily factor. We can figure out what to do once we do that. These numbers are relatively small, and it won't make it difficult for us to deal with them. So now the 3 times the 4 is the 12. So by the power rule, nice simple derivative, 12x squared. And then, of course, the 2 times the negative 9, a negative 18x. So now, of course, we can just factor the 12, and we can factor the x from each term. 12x, so that leaves us an x. And then we have minus 18 over 12 here. So when we look at this, we're thinking, okay, well, this is very simple. And then if we like, let's go ahead and extend this 12x. Of course, if we divide by 6 upstairs and downstairs, we just get x minus a 3/2. So again, we're not dealing with any infinite discontinuities or problems. And so we can now look for zeros of the second derivative. Okay, remember, when we look at the zeros of the second derivative, or maybe possibly infinite discontinuities, what we're trying to figure out is the sign, because we know from our pre-calculus techniques that a sign will change possibly for a function at a 0 or at a point where it is undefined. Okay, so we want to exhaust all of those possibilities so we can simply assess the sign of the second derivative. So now we have moved from the realm of the first derivative into the realm of the second derivative. So we'll say this equals 0 if and only if x equals 0 or x equals 3/2. So just like if you were in your pre-calculus class, what we do in the calculus is that we don't assign a particular inequality to the function we're analyzing. We simply figure out the sign based upon the so-called boundary values. So we're creating the inequality just by saying, okay, we don't want to know just where it's positive. We want to know where it's positive, and we want to know where it's negative if that's, if that happens. So we're covering all the bases. And then, of course, you know how you can say, well, the problem tells us greater than 0, so we select all those intervals that give us this. Here, we just take all the intervals and analyze what's going on. So it's the same procedure. We just have a little bit different conclusion. So now we have our 0 and we have our 3/2. And remember, what we always do is we go back to this nice factored form that's easy to analyze. And so, of course, if we just take a number much bigger than 3/2, like 100, we clearly get a positive sign. So, and of course, these are both multiplicity 1. So let me just write that down. Multiplicity 1. Multiplicity 1. Sometimes you don't even write that down. It's right up here and you're thinking about it. But let's just recall that if we don't get very diligent about how we look at multiplicities, it could really affect our analysis of sign. So now, of course, we have positive, and then of course we have to cross in both cases because of the odd multiplicity. So that makes the analysis of sign very simple. So we have plus by the concavity test or test for concavity, we can just do like an upward concavity symbol. And then we have a negative derivative, so we have a downward concavity symbol. And then, of course, we have positive, so we have an upward concavity. Now, of course, we have continuity throughout this set. And what we're seeing at this point is that the concavity changes at 0 and 3/2. So we have points of inflection defined here. So now we can say points of inflection. Points of inflection will be what? 0, comma, f of 0, and 3/2 f of 3/2. Now, of course, before, we'll go back to our rendering of f. This is just x cubed times x minus 3. So let's go ahead and figure out what these points are. Not too difficult there. F of 0 is clearly 0. So we have that. And then f of 3/2, we'll just substitute. So we have 3/2 quantity cubed. And then 3/2. So we can write the 3 with a 2 downstairs. So that would just be a 6 over 2. 2 times 3 is 6, right? So that gives us what? 3 cubed, which is a 27, and 2 cubed is an 8. And of course, here 6 from 3, that's a negative 3 over 2. So that'll give us what? A negative 81 over 16. So we have points of inflection, just to catalog these, 0, 0, and we have 3/2 negative 81 over 16. So this provides so much more detail. And if you think about it, when you would draw your polynomials in the prerequisite courses, you would apply a shape. It just made sense to do so. And if your graph was poorly drawn, you thought, well, I could do better than this. I'm sure it doesn't look this way, but the fact that you have a nice continuous function that has differentiability, the curve is very pleasing when you fill in all the details from the derivative. And now, of course, we can catalog the concavity just as we used here. We've got it on the number line, but let's just write it. So we'll say upward concavity, or concave upward, however you want to do it, upward concavity. And we'll just list the open sets. You could certainly close them. That's no problem. So we have what? Negative infinity to 0. And we have 3/2 to infinity. And for downward concavity, we have what? Well, let's just see. We've got what? Just right in between 0 to 3/2. Now, as we saw before, when we looked at the first derivative test, we had critical numbers of f, critical numbers of f. And if you recall, we had 0 and 9 over 4. Okay, but of course we don't get anything here, and of course the f double prime of 0 is 0, but we have the first derivative test that just shows that there's no relative extremum there, so we're done with that. But just to remind you, the critical numbers of f were 0 and 9 over 4, and we determined that f of 9 over 4 in this case, which was, to remind you of that, was negative 2,187 divided by 256, gave us a relative minimum, which we can now assign to be a minimum of the function due to the end behavior and the lack of any other critical numbers that would give us any information. We've exhausted all the possibilities, so to speak. So now we're thinking, okay, well, if we apply the second derivative, do we match what we got with the first conclusion from the first derivative test? So let's do f double prime of 9 over 4. Okay, so now we just go back to our easy calculation here. Our second derivative is factored this way, so it makes it easy to analyze it if we're going to do this. Clearly, if we differentiate, we go here. But when we're trying to evaluate, this is so much easier. So we're going to have 12 times 9 over 4. And we just have to figure out the sign. And then we have 9 over 4 minus 3/2. Well, this is an easy analysis. Of course, this portion is positive. And of course, 9/4 exceeds 3/2. So this is positive. So this is clearly greater than 0. We don't really care what the actual number is. We just need to know its sign. So this implies f of c is a relative minimum. So it doesn't matter which test you use. What's important now is that you see if you're going to utilize the second derivative test for the analysis of extrema, you go through the first derivative clearly to get to the second derivative, but the first derivative gives you the critical numbers. And then, of course, you don't really divorce yourself completely from the first derivative or the first derivative test, because if we had just gone ahead and said, well, f double prime of 0 is 0. So let me just write that down. F double prime of 0 is 0, okay? And then this just says no conclusion. Right. So if we had just avoided anything with the first derivative test, that is, we would have to return to it. So if you had just looked at this, okay, well, we know that f of 9/4 in this case is a relative min. So let me just go ahead and characterize that for what it is. It's the c, but let me just write it as 9 over 4. Since we know exactly what that number is. But now for the f double prime of 0 being 0, there's no conclusion with the second derivative test. So what we did was use first derivative test. So the idea here is that we see that both of the derivative tests are kind of married to each other, because you may have to use one when the other doesn't work. The first derivative test always working. And then, of course, if you want to analyze shape vis-a-vis concavity, you need the second derivative. If you want to then characterize your points of inflection, you analyze the sign convention from the second derivative and take into context continuity at these points. So I like this, how now you can see that with curve sketching, all the ingredients are here. We have the extrema, we have the shape, we have increasing, decreasing. You can throw in some intercepts, and then you've got more than enough information to get a really, really reasonable graph. I mean, we could do amazing things before the derivative in the pre-calculus prerequisites. It's amazing what we could do. And most of the analysis having to do with the calculus was more intuitive. We didn't have all the arithmetic, but we thought the end behavior makes sense. We just look at that leading term. So again, just look at this as being the complete story. That is, with all of this information, we can do exactly what we need to do to have a complete and accurate analysis of the function. Okay, so now what I want to do is I want to look at a trig function. Now, many times in the prerequisite courses, you utilize the transformation techniques. Now, of course, you can combine transcendental with trigonometric, but it's kind of more, I guess, instructive when you think about what happens in cases where you had no calculus and you simply used transformations and you made your way to a reasonable picture using pictures of the parent function that were reasonably accurate. So what we want to do now is look at a pre-calculus type function and see how the calculus verifies what we thought was a very reasonable sketch. So I would like to do one of those. So here's a function. This will be a very instructive exercise. So we have f of x equals 2 times the cosecant of 3x over 2. Now, to make this analysis maybe a little bit more doable, we will restrict the value of x to that of the unit circle, 0 to 2 pi radians. So often when you deal with certain trigonometric functions, you look at a period, and then you analyze that, and then know that that period will be replicated throughout the domain. Now, what I would first like to do is I would say analyze using first and second derivative. So many times, like I said before, the question might say, well, find points of upward and downward concavity. But what I want to do is analyze each derivative like we did in the previous example and see how the results compare, noticing what we get from one that we don't get from the other, and then how they overlap. And then plus we may have some very interesting functions that have objects that the previous function did not, and we want to see how that enters into the calculation. Many times, as I've said before, we forget about the prerequisites and think that the magic is all with the new objects. We think, well, we've got the derivative now. We don't have to worry about other things, entering into the picture. So what I want to say, or what I want to do, is look at this as a pre-calculus problem and then think about this as a differential calculus problem, okay? So first, let's think of the parent function, which is the cosecant function. So we have cosecant of x, and we can do the H compression, horizontal compression. Again, we're multiplying x by 3 over 2. So H compression, make it 3/2 smaller, H compression by 3/2. So just look at this as a pre-calculus problem and just see what we get and see how the calculus supports that. And then, of course, we're going to do a V-stretch, even though we know this has vertical asymptotes. We still abide by this. So V-stretch by 2. It's like, well, multiplying infinity by 2, it doesn't do anything, but it certainly, if you have relative extrema, it can move them around. So we get what? 2 cosecant 3x over 2. Okay, so what we want to do is think, well, what happens to the objects of the standard cosecant function? Now, I just want to draw over here the parent function, just a period, and that's what we're going to work with. So when you deal with the parent function, you have a period of 2 pi. So you have x equals 0, you have x equals pi, and you have x equals 2 pi as vertical asymptotes, and then you've got a 1 and you have a -1. And so when you draw it, you're just using the fact that you're reciprocating the sine function. And then, of course, we notice here, let me extend this a little bit. just kind of run into that. There we go. Probably should have written the asymptotes in different places. And then of course, we don't need to extend anymore here, but this would just keep replicating like this. So this would be the parent function. So we would want to know, well, what's this point here? This is what? Pi over 2. And of course, this is 3 pi over 2 here. So we would want to know what happens to these 2 points and also what happens to the vertical asymptotes. So this is what we call the parent. And this is exactly what you did in your prerequisite courses. So now let's put everything down. We've got what? X equals 0. We have X equals pi. And then we have X equals 2 pi. So when we do the compression, we're just dividing by 3/2 or multiplying by 2/3. So X equals 0 doesn't change. So we get X equals 2 pi over 3. And then, of course, multiplying by 2/3, we get 4 pi over 3. So that gives us a new period, which is 4/3 pi, and we'll verify that is indeed correct. And then, of course, what's going to happen to the point? We've got what? Pi over 2, 1, and we have 3 pi over 2, -1. So I'll just draw an arrow there. And so, of course, we're going to do the same thing here. We have what? Pi over 2 times 2/3. So this implies, in this case, the 2's absorb. So we get pi over 3, 1. And here we have the 3 pi over 2 times 2/3. The 2's absorb. And we just get 3 pi over 3. And I'm going to keep writing it that way so we all have 3's in the denominators. That'll make it a little bit easier to do the arithmetic. Now, when we look at this, the next thing is to do the V stretch. Of course, the asymptotes don't change with the V stretch, so we'll just write these down. So that's where we have the infinite discontinuities when we were talking about infinite limits. And then, of course, with the V stretch, the y coordinates get multiplied by 2. So we get what? Pi over 3, 2. And we get 3 pi over 3, -2. Okay, so this would characterize the new graph. But remember, in this analysis, we have this interval here. Okay, so we always have to remember that. Now notice, if you think about this in terms of pre-cal, we have the standard period is 2 pi. And if we divide by the coefficient of X, which is 3/2, that gives us 2 pi times 2/3, which gives us 4 pi over 3. So this is in agreement with what we have here. So we're going to have an additional piece that we need to work with. So notice here, and this is what's going to exhaust everything. So we've got the next vertical asymptote will just be the 4 pi over 3 plus the 2 pi over 3, which gives us the 6 pi over 3, which is the 2 pi. So that will extend to the next vertical asymptote, so we can actually complete the graph in this given interval. So now notice, and this is what we had before. We just want to use this picture here and adjust it to the new transformation. That is the transform graph here. We want to use this. So that's how we made our way. And we were convinced that this was fine when we reciprocated the sine function. You know, when you divide by 0, you get the vertical asymptote. 1 reciprocated is just 1. -1 reciprocated is just -1. So you get these kinds of points. So that was not a surprise to us. And we didn't think that our pictures were bad. We thought they were good. So now let's go ahead and draw this. so we can put in all of our thirds and make it easy to draw. So again, we extend to, in this case, 6 pi over 3. And of course, that's going to give us a 5 pi over 3 as a point. So we can just put thirds here. So we have 0, pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3. So we'll just go ahead and label these. And then we have 3 pi over 3, 4 pi over 3, 5 pi over 3, and then 6 pi over 3. So let's draw in our vertical asymptotes. And then at 4 pi over 3. And then we'll extend to 6 pi over 3, which gives us 2 pi. So we want to extend to the entire interval. So now, of course, we have 1, 2, and then -1, -2. Now, if you like, we can label these x equals 0, x equals 2 pi over 3, x equals 4 pi over 3, and then x equals 6 pi over 3. So again, we just have our cheat graph up here and draw it. And then we go here, do the same. And then back to here, 5 pi over 3, just copying that, replicating that curve right here. So when we look at this, this gives us the function f of x with the pre-calculus techniques, 2 cosecant 3x over 2. That's the pre-calculus derivation that we would use. And of course, how much information you put here is just, you know, whatever you are requested to do. So we have a horizontal compression, and we have a vertical stretch. And so that changes the parent function. So when we look at this curve, and this is very instructive, and this is what I have told many students in the calculus, you can't forget the way you define the trig functions, especially the functions with the vertical asymptotes, because that is your definition, that is your arithmetic. And so if you don't have the knowledge of this, then it's very difficult for you to analyze the arithmetic in the derivatives of these functions. So this, as I've said many times, you take everything you learn in the prerequisites, you take that to calculus, and then you add the new information, then you combine all of that, and that gives you the entire picture. So when we look at this, ladies and gentlemen, it looks, at least from what we've drawn, that here in these sections, we have the upward concavity, and here we have the downward concavity. However, there are no points of inflection. That is, where the concavity appears to be changing, we have an infinite discontinuity. So again, when we drew this picture in the pre-calculus, we drew it like that because it made sense for it to look that way if we thought about the shape of the sine function. So we inferred a shape to the curve, an upward concavity here, a downward concavity here. And then we notice, well, decrease, increase, increase, decrease, decrease, increase. So again, if our picture is correct, the calculus should support that. Now, it's very convenient that we had this technique using transformations, but the calculus is so much more far-reaching. It's going to work on any differentiable function. So now what we want to do is analyze the function f here utilizing the first and second derivatives, as I've said here. So look at this as very essential pre-calculus material. And then now let's apply some calculus. So let's go back to the function f of x. So f of x equals 2 times the cosecant of 3x over 2. And we have x living between 0 and 2 pi. So as I've said before, we don't want to forget our pre-cal. So we've already done that work. And let's just note, infinite discontinuities. Infinite discontinuities. We'll just write the vertical asymptotes. We have x equals 0. X equals 2 pi over 3. X equals 4 pi over 3. And x equals, in this case, 6 pi over 3. So these are the so-called VA, okay? So we don't want to forget that, because when you analyze the sign of the derivatives, even though these will not come up as critical numbers, they are boundary values, and they do impact the sign of the function. So that's what I'm talking about. We take all of the information from the pre-cal into the calculus to complete the analysis. So now let's just remember this. So we've got these kind of, infinite abyss as we move through these to be able to determine sign correctly. Now, and one other thing, let me just mention this. What we see here, relative extrema, relative minima, relative maximum, okay? These look like they occur at horizontal tangents if we drew our graph correctly. So I didn't even mention that. So that's another thing that we should be able to see from the calculus. So let's do our derivative. So we have f prime of x. Of course, the 2 we just leave out to the left. It's just there. And then, of course, we take the derivative of the cosecant, which is the negative. So we'll just put a negative here, negative cosecant cotangent. Good old calculus. So again, that gives us the derivative of the outer function, and the derivative of the inner function is just 3/2, in the sense that 3x over 2 derivative is just 3/2. And so now the 2's absorb. And let's look at what we have here. We've got a negative, so we have a negative 3 cosecant 3x over 2, and a cotangent 3x over 2. Now, often when you're doing analysis, you don't have to do this, but when we're looking for critical numbers and we're looking to analyze, we sometimes feel more confident when we write in terms of sine and cosine, so that can showcase or at least display multiplicities. So let's go ahead and rewrite this with sine and cosine. So here we have a negative 3. And this is so important, ladies and gentlemen. We have this negative here. This will impact the sign, okay? So we don't want to forget it. The 3, no big deal, but the negative is extremely important. So now we have what? 1, let's just write this 1 over sine of 3x divided by 2. And then cotangent is what? Cosine over sine. So we have cosine 3x over 2 sine of 3x over 2. Now, this is opening the door to much greater analysis. So now we can just put everything together. So we have the negative 3, we have the cosine 3x over 2. We know what the sine is giving us as far as infinite discontinuities. That's what we already know, but that occurs to a second power. So we have sine of 3x over 2 quantity squared. So what we're seeing is that the infinite discontinuities have multiplicity 2. So we'll say equal to 0, question mark. As part of the analysis, we'll say infinite discontinuities. Well, I'll write that out, discontinuities. This has multiplicity 2. So that will change the way the sign interacts with the asymptote as far as on either side. The sign does not change, at least for that particular factor. So that's important. And then, of course, we're thinking we appeared to have horizontal tangents. So this means that the numerator would be 0. So we'll just say that f prime equals 0 if and only if 3x over 2 would just be an integer multiple of pi over 2. That would be zeros of cosine. So we have 3x over 2 will just be, and of course odd, right? 2n plus 1 pi over 2, because we remember we don't want even multiples. That would just absorb and give us, right here and where we got plus or minus 1. So that's no good. So now, of course, the 2's absorb. And we're not going to be surprised by what we get. We'll get x equals 2n plus 1 times pi over 3. So this gives us something that's not surprising. So let's just check this. Let's say we're interested in this interval. So we have n equals 0. So we get x is what? Pi over 3, not a surprise. N equals 1. So we get x equals 3 pi over 3. And then n equals 2. So that'll give us a 5. So 5 pi over 3, x equals 5 pi over 3, which is exactly what we see here. So this is identifying these horizontal tangents at pi over 3, 3 pi over 3, and 5 pi over 3. So if you do not have the analysis from the pre-cal, your derivatives will not make any sense. You're going to have to go back and figure that out. And this is what I'm talking about. When we define the trig functions, we define them via the unit circle, and all that arithmetic flows from the unit circle. So this is actually just as important as the calculus, if not more so. So there we have our horizontal tangent. So now we see these as critical numbers of f. Critical numbers of f by definition. But that doesn't mean we can discount the infinite discontinuities. Even though they're not in the domain, they will impact the sign. So now let's do our number line analysis. So it's kind of like, all right, well, it looks the same as we had before. So we have the 0, and we'll just do them in order. Pi over 3, and then 2 pi over 3, infinite discontinuity. 3 pi over 3. Don't reduce anything. You just do like your professor said in the pre-calculus work. Don't reduce things. Keep everything with the same denominator. 5 pi over 3. Well, back here. And then infinite discontinuity, endpoint. So again, we're analyzing f prime. So the way we do this is we just figure out what happens at the beginning, and then we can use the multiplicities. And notice here, this occurred to odd multiplicity. So we say multiplicity 1. So what do we say here? We say cross. And here we say touch. So that is really important when it comes to doing inequalities, and it makes your work so much more efficient and actually more accurate. So now notice, if we go back to our function here, and we just take, say, something like pi over 6 here, where both sine and cosine are positive, we have a positive contribution here and a positive here, but the negative here throws the sign into the negative category. So we start here, but notice at the pi over 3, we cross, so we're negative, we cross, but then at 2 pi over 3, we touch because of the even multiplicity, so we're still up. But then at the 3 pi over 3, we're here, so we have to cross. And then at the 4 pi over 3, that's an infinite discontinuity where we touch. And then at the 5 pi over 3, we're back here where we must cross. So that analysis gives us what we need, which exactly parallels the picture that we've already drawn. But this analysis is not possible unless you understand the rudiments of the cosecant function and the transformed function that we talked about. So these problems necessarily, just like when we did infinite limits, we'd have to think about how we constructed these functions and figure out where is it infinite, positively infinite, negatively infinite, and think about that when we did the right-sided limits, right and left-sided limits, or just one-sided limits. That was imperative. So we're seeing the same thing here. We really can't get away from it. So now we have negative or decrease. So we have decrease and then increase. So plus, increase. So this gives us what? Relative min. F, we already know what it is. We don't have to compute it. F of pi over 3. And then, of course, infinite discontinuity. Now plus, so increase. Then we cross, negative, decrease. So we're increasing and then decreasing. This is a relative max by the first derivative test. We already know what that is. F of 3 pi over 3. We know that value. And then, of course, here we're doing what? Decrease again, because we're still negative. And then increase. So decrease, increase, again, a valley, relative min, F of 5 pi over 3. Now we already know what these values are because we computed them with our what? Transformation, 2 and negative 2. We don't have to do that again. I mean, don't do that. I mean, you're wasting your time. You already know what they are. So here we've got what? We have 2, we have negative 2, and we have 2. So we got the relative extrema with no problem. But of course, now we know we don't have a max nor a min because the function blows up infinitely and negatively infinitely. So I mean, positive infinity, negative infinity, we just have relative extrema. But what's nice about this is if we go back and make the comparison, just kind of line it up, decrease, then increase, increase, decrease, decrease, increase. So this parallels exactly what's going on here. And notice as we work through the asymptote, increase, increase, that's where this lines up. And then as we work through this asymptote, we're decreasing, decreasing, as we see here. So this type of analysis requires the analysis of the functions and then keeping track of the multiplicity. Of course, if the multiplicities are all odd, it's even easier. You just cross every time and you don't even really have to think about it. As I instruct my students and as I instruct you all, especially in the prerequisite courses, I'll say, make sure you get the first one right because that's going to, characterize the rest of them. So check out the first one that you analyze and then move through using multiplicities. Now, the last part that we need to do is to see that we can verify the concavity that we drew in the last problem. So let's do that. That is when we did our pre-calculus technique. Now, what we want to do, and let's just choose the easiest one because, we're going to be lazy about this. We're just going to go up to here and use this one because it's not factored and we don't want to spend too much time. So let me write this down while we have this in front of us. So we'll say F double prime And I'll just put this in the parentheses, -3 cosecant 3x over 2 cotangent 3x over 2. We're going to take the derivative of that. So we're using the most hospitable form of the first derivative to do the second derivative. We don't want the analyze part. That would be crazy. We only do that to figure out sign. So just remember, as you work through and as you make a function more hospitable for understanding critical numbers or boundary values, that's necessary, but that's not the form you want to differentiate. You just go back to the form that'll make your life easy or easier. So now let's go ahead and factor the -3 because it's just in the way. And let's note that we have a product here. So put a little dot there. So we have to use the product rule with the chain rule. Product rule with chain rule. The beauty of the calculus is that it verifies everything we've done before. And so that should make us all feel better. So now we take the derivative of the cosecant, which is the negative cosecant cotangent. So we get negative cosecant 3x over 2 cotangent, but then we have an additional multiple of cotangent, so we have cotangent squared. Let me say that one more time. The derivative of the cosecant is cosecant cotangent, so we just write cosecant cotangent times cotangent, which gives us 2 copies of cotangent. That's all. Now, the derivative of the cotangent is the negative cosecant. And of course, here we go, chain rule. Everybody's thinking, oh, Professor Ron, you left out the chain rule. Yeah, we got to have the derivative of the inner function. That just kind of always sneaks up on us. So the derivative of the inner function, of course, is 3/2. That hadn't changed. Now, when we look at this, we have the derivative of cotangent, which is the negative cosecant. Then, of course, with the chain rule. But that's going to give us what? 3 copies of the cosecant. So we have negative cosecant cubed 3x over 2 times 3/2. Now, I have to be the first to say that the derivatives are easy to do, but they are easy also when you forget things. So just be careful that you apply your derivative formulas correctly. Have your little card of derivatives if you need that from the formula sheets, and make sure that you write them correctly. And don't forget the negatives. Now notice here, we have a negative here, we have the 3/2, we have a negative here, and we have the 3/2. Now let's just go ahead and move that out first, and then we'll look at what we've got left. Now, what's interesting about all of this is that if we break it down into steps, it'll be a little bit easier to analyze. So we have the negative 3/2 times the -3. So that's going to be 9/2. And now we've got the cosecant 3x over 2 cotangent squared 3x over 2. And I'm going to do a little smoke and mirrors here. I'm going to write this cosecant as a first power of cosecant times the second power of cosecant, like that. Okay, so now we'll do our factoring again. This will come out, and this will come out. So this is what I'm talking about using the algebra from the prerequisites. Makes the work very simple. So we have 9/2 cosecant. You never thought a problem that looks this simple would take this much analysis, but they do. They really do. The trigonometry is always going to be more complicated because the functions are more complicated. They're transcendental. So now we have the square of the cotangent, which certainly makes the sign analysis easy. And then we have the square of the cosecant. Okay, so this is what's nice about this. Notice the cosecant is squared, Okay, so it's what, in this case, 2 or greater, right? I mean, and then of course, squaring the 2, 4 or greater. This is always positive. This is just non-negative, but the sum is positive. So here, we don't even have to worry about it. It's not going to change the sign. This is positive. So we're done with that. No negatives to interfere with signs. That's positive. Done with that. Now, the only thing we have here are the infinite discontinuities. This is never zero. The cosecant is never zero, but it can have an infinite discontinuity. So we write down the infinite discontinuities that we already know, discontinuities. And that'll give us the 0, the 2 pi over 3, the 4 pi over 3, and the 6 pi over 3. Again, that makes the cosine, or excuse me, the sine 0. So now let's write this down. So we've got 0. We have 2 pi over 3. We have 4 pi over 3. And we have 6 pi over 3. So now notice here, this is always positive. The 9/2 is positive. And then, of course, we just think of, the sine function in this interval where it's positive. It's always positive in the upper arc, or at least in the first half of the period. So we've got positive here. And notice again, multiplicity 1. Multiplicity equal 1. Okay. So here we have, in this case, positive, cross, and we're done. So we have plus, concave upward. We have negative, concave downward, plus, concave upward. And this is F double prime. So notice here, we go back to our picture of choice from the pre-calculus, and we compare. Again, get these lined up. 0 to 2 pi over 3, concave upward. 2 pi over 3 to 4 pi over 3, concave downward. 4 pi over 3 to 6 pi over 3, or 2 pi, concave upward. Exactly what we drew in the pre-calculus mathematics. So what we're seeing is that the analysis is more complicated. And of course, we found, and you think about this. When you are doing graphs based upon a parent, you are assuming that the parent has been drawn correctly. Okay, so that was a big plus. And what's important about the parent is that we understand the arithmetic when it comes to what? Zeros, because we have the unit circle, and infinite discontinuities. Okay, we understand that because we have the vertical asymptotes, which are at least defined in an intuitive sense in the pre-calculus classes. So what we're seeing is that the arithmetic of the second derivative supports all of that, but now we can see that the second derivative and first derivative can always be applied universally to differentiable functions to give us what we need, always. So that is the superior nature of the derivative, but it does not discount all of the information that we learned before, because in order to analyze this, you need that. So now notice, the concavity changes here, but these are not points of continuity. So this implies no points of inflection. No points of inflection. Of course, if you had one, you'd have infinitely many of them, because this would just repeat, every 4 pi over 3 radians, because that's the period. And now, of course, we have upward concavity. Let's just write this, upward concavity, and we'll give the open sets. Upward concavity will be 0 to 2 pi over 3, and 4 pi over 3 to 6 pi over 3. And downward concavity will be from 2 pi over 3 to 4 pi over 3. So what's interesting about this particular example and the previous one is that the analysis of the derivatives, the domains, infinite discontinuities, critical numbers, multiplicities, sign test, all of that, it's all intertwined. And so when we think about curve sketching, these are the final ingredients that, again, I've said many times that we did not have in the prerequisite courses. So as you continue, and you should also look in the lecture notes, you will see other functions that are analyzed in a similar way, where you look at the first and the second derivative, and then you can see the requisite algebra that is required. Many of you discuss examples about how it's hard to deal with some of the algebra with the negative exponents and things like that, and I have examples of those. But what's important is that you take the time to analyze the algebra and check what you're doing. That it is no problem to make a mistake while you're studying, of course. You work through that and you shore up the algebra. But I just want to make very important connection to the prerequisite, that the prerequisite information is very important. It opens the door to the analysis of the derivatives, because you can't leave that out of the picture. If you only look at critical numbers, then you don't have half of the information. You must use the information from the original function, the way it's defined. So this was so important to actually talk about this as a prerequisite model. And then now we verified that the pictures we've been drawing have been extremely, extremely accurate. I mean, you can't improve upon this. And the calculus verified every bit of this. That is, we have the verification through the first derivative analysis, and we have the verification through the second derivative analysis. So as you work through these particular examples, don't discount the first derivative. Go ahead and analyze the first derivative. Make your way to the second derivative. Of course, if you're just focused on one certain aspect, you still have to look at the first derivative as being a very vital transition point, because the transition to the second derivative requires that the first derivative, be done correctly. And so if you're going to use the second derivative test, you need accurate derivative, you need an accurate critical numbers of f. So take this opportunity to refresh your memory with the pre-calculus techniques, especially the trigonometric functions, and see how that intertwines with the calculus that you have learned about the second derivative. And then, of course, in the next lecture, we're going to focus on limits at infinity. And I don't think you're going to find that to be any more difficult than the infinite limits. And in many ways, it'll be very, I think, a little bit easier, because with the limits at infinity, you do have a theory that mimics some of the limit theorems that you had at the beginning of the course. So that I think will make the transition fairly straightforward. And again, we have the intuition from the rational functions, which will be a big help. So that's all I have to say about this. We'll see you soon. Thank you.